Okay, so we're Team 75, and this is our presentation for the Mars Cargo Mobility System overview. So the objective of this project was to design a Mars rover that can follow a line, carry a load of cargo, detect a magnetic beacon, climb a hill, accelerate to a specified speed, traverse obstacles, and maintain that desired speed until the line terminates. And we were supposed to use the provided materials that we were given, which included a diverse assortment of Legos to build the frame and chassis of the robot, various sensors to detect the data that we needed to complete the course, and the Raspberry Pi, Rick Pi, and Grove Pi, which stored our code and also could interpret the data of this, which the sensors were reading. And this was the course that we had to run through. So for project management, we scheduled meetings in coordination with our Gantt chart, which is shown right here. So you can see that our top priority was to build a robot structure, just like the frame and everything. And then we had to program the robot. And I'd say that this is the one thing that probably changed over the course of our construction process. And because the programming really took up to the week of the evaluation, but we were definitely testing it pretty much throughout the whole process. And the project ended up taking more time than we expected because we had to evaluate a lot more alternative solutions that we didn't account for in the initial Gantt chart. So we scheduled more meetings. And we found some brainstorming techniques helpful, like random entry, to give us ideas such as scorpion and grocery, which were keywords that helped us in our design process, because the scorpion kind of gave us a idea for how to carry the cargo kind of on the back and above the robot, like a scorpion's tail. And grocery helped us determine how we were going to use the back wheel, or the back wheels, I guess. And we decided to model it after a shopping cart, which can go in every direction and has minimum friction. And the last thing that we tried to do was fairly allocate the work between all the group members and make sure everyone did work at home so that we could work efficiently and effectively throughout the whole process.
Now I'm going to be going over the design philosophy and more specifically the mechanics of it. First, I'm going to start off with the final design. For the body, we had it with 3 wheels, 2 large wheels in the front and 1 small wheel on the back. The wheel in the back is where we used the grocery cart idea because, like Lucas said, it can spin in any direction and it's slightly elevated, which helped raise the back end. We also had it as front wheel drive, and the cargo holder, which is another part of where the Scorpion came in, had 4 sides. It had the base and then 3 side walls. And overall, it had 3 motors, 2 in the front controlling the front wheels, hence the front wheel drive, and then 1 in the back controlling the cargo holder. And for sensors, we used a color sensor to follow the line. We used an ultrasonic sensor to sense the hill, and then we used an IMU for the magnet and the cargo drop. So now I'm going to be talking about the main changes we made. First, we went from a claw drop to a dump. The first picture you can see is the original claw drop, and we decided to switch from that to the pictures you can see on the right, which is just the dump, because it was a lot more complex, it was harder to work with, and it used a lot more materials. So rather than focusing on making sure the orientation was proper, we wanted to make sure that we had a simpler design that we knew would work and we knew could integrate better. We also switched from 4 wheels to 3 wheels. That kind of goes more into the Scorpion design again. We changed from 2 back wheels to 1 back wheel so that turning was easier, and it helped raise the back a little bit. And then finally, we switched from a line finder to a color sensor because the line finder was having trouble calibrating, and the color sensor was a lot easier to use and code. And finally, this is a video that demonstrates the line following and the magnet sensor and cargo drop.
All right, so now kind of onto how we were able to accomplish all this with the code. It really boiled down to like three main basic elements that we needed to figure out. First was line finding, second was the cargo drop code, and then finally it was the speed control code for the speed control track. And so you can just see like kind of an overview of what our final code looked like on the right there. And then here we can also see a flowchart of what the code looked like. So you can see we can start, and then once it senses black, this whole thing is the line finding algorithm. So if it senses black, it goes forward, and if it doesn't sense black, then it'll turn, and then it'll keep going through that until there's a keyword interrupt, so we stop the program ourselves. And then obviously once the magnet senses a magnitude that's large enough, like it's over a magnetic beacon, it will go through the series to enable the cargo drop function of our rear motor itself. And so then kind of going into more detail about how we were able to follow lines and find them, we ended up going with more of like a zigzag on and off the line sort of method of transport. And this happened because we ended up going with a single color sensor rather than a double line finder, like was also an option. And so what this allowed us to do essentially was to, when it sensed black, it would turn to the left, and then when it didn't sense a black color on the floor, it would turn back to the right. And so that sort of zigzagging back and forth allowed us to actually get forward motion in itself. And in this, we were sort of ran into problems because we had this zigzagging motion. It had a harder time when the surface wasn't exactly flat. So like when we had to go over the hill or go over an obstacle. And so you can see the first set of code that's on the right, that's the sonar code that we added to help us actually get over the hill. And so what we ended up adding was a ultrasonic ranger to the front of the robot. And when that sensed a distance that was less than 2 centimeters, which was about the height of the sensor on the robot, it knew that we must have been at the hill because that's the only time on the track that there was actually an incline. And so once it sensed that, it would increase the speed so that we were able to have forward motion at a high enough velocity to actually propel us over the front of the hill. And the other part of this problem with the zigzagging motion was that it had a really hard time getting over obstacles. And we sort of solved this problem by adding in a count, and you can see on the right, the count greater than 75. And so once it turned left and right, searching for a line for more than 75 times, it would again increase the power to sort of propel us over whatever obstacle was blocking our forward progress. And then finally, we get to the cargo drop. And here we used the IMU to sense where the magnetic beacon was. And this presented sort of a challenge for us because the IMU returns a vector quantity, which didn't really help us because we didn't know exactly which coordinate we should be looking after, if it was the X, Y, or Z. So we ended up taking a magnitude of all those values. And when it reached a magnet, we realized that the magnitude got larger. And so you can see in the code on the right, once the magnitude got over 100, we would go into our cargo dropping mode. And we did this by going forward a certain distance to allow the robot to actually travel so that the cargo would drop over where it was supposed to. And then once it got there, we also had the problem of, well, how far do we run the motor? And we solved this by setting motor limits using the encoders that were actually installed inside the motors that we were using for the cargo dropping mechanism. And so it equated to about like a 75-degree angle that the motor had to run to. And so you can see there, the motor limits were 35 and 100. And then the final aspect of our test was the speed control track. And here we had to do a little bit of math because obviously we can't just say the drive motors need to go 30 centimeters per second. And so we ended up using the degrees per second feature that was included in the Lego motors, but we had to figure out how to correlate that to a centimeters per second like we wanted to see in our actual demonstration. And so we used this conversion where we knew that the diameter of our wheel was 7 centimeters, so the circumference would be 7 pi. And so you can kind of see that equation there to figure out how many degrees per second and how it correlates to centimeters per second. And once we figure out how to get to that speed, we also need to know how long it should go to that speed. And so that's the second equation you see on the screen, where it's 250 centimeters divided by 7 pi over 360. And then on the right, you can see the bare code. And then also we added a references for when we wanted to input the speed, so that we didn't have to remember all these, complicated numbers. We could just have a set guideline that we could base our actual degrees per second input off of.
Now moving into the more positive and negative attributes of the robot. First of all, we have these two videos which kind of show a positive and a negative attribute that are paired. So the first would be the magnet detection, which was a positive for our robot. And here you can see when we placed it directly over a magnet, it went forward a small amount, stopped, and lowered the cargo hold just as it was supposed to. Unfortunately, in this video and in the video on the right, you can see a more negative attribute in that the cargo hold itself actually knocked over the cargo, so it couldn't maintain the correct orientation, unfortunately. But after this, we have another pair of positive and negative attributes that are linked together, which would be the line following. And in this video, you can see on a straight line, it does really well at doing just as the code wants it to, where it goes forward and will swivel back and forth just a little bit to keep it on the black line and centered. And then in the video on the right, you can see where we ran into problems. So when we went around turns, which was something our robot was not super great at, especially on this turn, which was a very sharp turn with a small radius right before the hill. Our robot couldn't actually get around the turn correctly and ended up at the bottom of the hill with the wrong orientation. So we were never able to actually use the code that we wrote earlier, where it would allow the robot to speed up and get over the hill, which was unfortunate. But another pair of positive and negative attributes, something that it did really well would be the speed control. And the speed test, it went just along the line as it was supposed to and reached the speed they wanted and stopped as it was supposed to. And on the right, you can see a negative attribute, which was the inability to get over the different obstacles. With the code we wrote that enabled to speed up after a certain amount of counts of it trying to go back and forth on the line, we were able to get the front wheels over, but we weren't able to get the back wheel over because it was too small for all the weight with the cargo on top of it.
This leads us now to areas for improvement. So obviously the main two that we identified were getting over obstacles and the turning radius. For getting over obstacles, when we were testing it before the actual test, it got over without any cargo. But once we had to load in the cargo to get over the obstacles, it wouldn't go over. And our solution would be to increase the speed for the code that we had written for when the obstacle gets stuck. And for the turning radius, since it couldn't make tight enough turns, we were going to increase the speed on the motors while turning. So increase both the forward direction one and the reverse direction motors.
That brings us to our conclusion, where we said that the robot did well in following the line along with maintaining a speed, which you saw in those two positive videos. But the robot did not do well with sharp turns and getting over obstacles. And we learned that time management and teamwork are crucial for success, just because it would have been a lot more stressful if we hadn't started the project when we did. And our team worked together very well, which led to results that we were all happy with. And we also, I think, come from pretty diverse backgrounds and skill sets, which were all very useful in contributing to the end product. And although our demo didn't go perfectly, we left the project with a better understanding of just like how to integrate computers and design and coding and all into one. And if we were to do this project again, we think that we would have a lot more success.